All right, welcome everyone. Today is a great pleasure for us to have Professor Jinhui Yan from University of Illinois giving us a talk about the application of his computational mechanics methods in manufacturing. Professor Yan got his PhD at UC San Diego, working with fluid structure interaction on the modeling aspect, and then he did postdoc at Northwestern. That's when we overlapped a little bit. But since then, he joined University of Illinois in the Department of Civil and Environmental Engineering. But I think his work is still very relevant to our Department of Mechanical Engineering. And because of his nice work, he won several honors, including 2 Young Investigator Awards, one from the ASME and the other from the US Association for Computational Mechanics. So without further delay, let's get the seminar started. Right.
Right. Thank you very much for the kind introduction, and also thank you for the invitation. Good afternoon, everyone. My name is Jinhui Yan. Thank you for coming to this presentation. So I know Michigan is a powerhouse for mechanics and advanced manufacturing, and I truly enjoyed the visit today, and I have a very good conversation with many people in the department. So it's really my pleasure to be here and to present some of my recent research progress in mechanics and manufacturing. So in today's presentation, I would like to show you a mixed diffusive-sharp interface approach we recently developed for multi-physics simulation and modeling, and I will show you its application to metal additive manufacturing. So this is a single detailed topic. I really want to dive very deep into the details of the method. However, before I do that, I want to give a view about what my research group is doing at the UIUC. So one primary focus of my research group is computational mechanics for metal additive manufacturing. So basically, we develop numerical methods and models to simulate all the aspects related to metal additive manufacturing. So we do feedstock modeling, and we also do process modeling and optimization. The overall objectives are first, of course, to derive the process structure performance relationship. I think this is still an open question in the field. And the second one is to achieve energy efficient printing process, because because the manufacturing sector is still one of the biggest energy consumer across the industry. And certainly, compared with conventional manufacturing technology, additive manufacturing is still slow and inefficient. So we also want to develop models to help achieve mass production. Specifically, right, my research group right now is working in 2 directions. The first one is how to produce high quality mechanical powders. So currently, one way, right, to produce mechanical powders is through the ultrasound metal optimization. So what you do here is you vibrate liquid thin metal film to generate droplets, and after those droplets are resolidified, I mean, they can be used for powder-based printing process, such as laser powder bed fusion or direct energy deposition. So recently, we developed a lattice Boltzmann method to directly simulate the details of the ultrasound optimization. So the model can directly quantify the particle size distribution for a given combination of vibration frequency and the vibration amplitude. This lattice Boltzmann method is implemented by using GPU computing. So as a computational person, I couldn't help emphasize how fast it is. So for the video you see here, we are using 10 billion nodes, and the simulation can be done just within 10 minutes by using GPU acceleration. Another direction, of course, is after you get the mechanical powders, right? How to model and optimize the process parameter to achieve high quality printed parts. So this is the focus for today's presentation, and this is the outline for this topic. Okay, so I will first briefly discuss the challenging of modeling and simulation for metal additive manufacturing. And then I will show you two existing approaches you can utilize to tackle this problem. The first one is interface tracking, which is a sharp interface approach. The second one is interface capturing, which is a diffusive interface approach. I will show you the pros and cons of those two approaches and show you why we want to develop a mixed diffusive and sharp interface approach. And then I will show you how to use this mixed formulation to develop a high fidelity thermal multi-phase flow model to simulate additive manufacturing process. And I will show you how we use the model to predict defect, surface roughness, and the powder splatter. And then lastly, I'm really excited to show you some preliminary results from a recent developed method. We call it coupled level set and enriched immersed boundary method. So personally, I think this method shows huge potential for many multi-physics problems, especially for the problem coming from advanced manufacturing process. So let's get started. So first, let me begin by saying that from the mechanics perspective, additive manufacturing process as the interface coupled multi-physics system defined by DOE. Okay, so in interface coupled multi-physics, the physical coupling mainly works over an idealized interface that is lower dimensional or narrow buffer zone, mainly through the flux, pressure, and the displacement boundary conditions. Classic example include ocean, atmosphere dynamics in geophysics, and the fluid and structure interaction in air elasticity. However, personally, I think simulating the multi-physics problem in additive manufacturing is way more challenging than those classical physics and multi-physics problems. So let me use this video to show you some of the challenges, okay? So what you see here is a selective laser beam melting process revealed by Argonne National Lab by using high-speed and high-resolution imaging. And you see that when the laser scans the material, right, the laser material interaction leads to very complicated material interface evolution. You see the so-called chemical instability, right? And you also see that a lot of gas bubbles are generated from the chemical. If those bubbles couldn't escape from the resolidified material, they become defects. So from the mechanics perspective, right, the challenge of modeling this process is how to accurately and robustly handle the material interface evolution and the associated boundary conditions. Because the material interface, right, especially the gas-metal interface, is the central location where the metal and physics take place. So on the material interface, right, you have the interplay between fluid, mass, heat transport. You have phase transitions, right, melting, solidification, and evaporation. And you have very large property ratios across the material interface. And you have variant topology interface changes, as you see from the video on the left. And most important, right, on those material interface, you have a set of critical Neumann type of boundary conditions that needs to be satisfied simultaneously, including laser heat flux, surface tension, Morgenshtern stress, and recoil pressure, and so on. So in computational mechanics, there are two approaches you can utilize to solve this problem, depending on how you handle the material interface evolution. The first one is interface tracking, such as arbitrary Lagrangian O'Leary. So this is a sharp interface approach because in this type of approach, the material interface is explicitly represented by a conforming and a deformable mesh. And in this type of approach, right, the boundary conditions I mentioned can be directly applied as a traction and the flux boundary condition on the mesh because you have an explicit interface. The advantage is that this type of method is very accurate per degree of freedom. However, in order to maintain an explicit interface, you can see you need to constantly perform mesh motion and remeshing. And given the topology changes you see from the previous slide, it's almost impossible to apply this approach to realistic printing process, right? The second type of approach you can utilize is interface capturing. So this type of approach has many variants, such as level set, volume of fluid, and phase field. Those methods are also widely used in the multi-phase flow community, right? It belongs to the so-called interface, diffusive interface approach. In this type of approach, the material interface is implicit implicitly represented by an additional scalar field. And in order to capture the interface evolution, you need to solve additional scalar partial differential equation. And in this type of approach, right, the boundary conditions, right, the Neumann boundary conditions are typically applied as a body force and terms in the conservation laws. I will talk about this later in detail. And the advantage is that they're very flexible. You don't need to do any mesh motion and remesh, and you can handle the topology interface changes automatically. However, the drawback is that because you don't have an explicit interface, right, it's not very straightforward to handle the laser material interaction, especially the multiple laser reflection in the paper. So now, given the advantage and the disadvantage of those two approaches, we feel that mixing both of them is the best way to go for metal additive manufacturing applications. So our goal is to explicitly track the moving gas metal interface without doing any mesh motion and remesh procedures. So this is how we achieve this. So we first utilize the interface capturing approach. In this case, it is level set method. So level set method essentially, right, is a sign distance function, right, which will give you the distance function from a material point to the gas metal interface. But we only use level set to capture the topology changes of the interface, and then we go to interface tracking. So basically, what we do is we explicitly extract a triangulation from the zero level set that representing the material interface. At first glance, you may feel that this is very complicated. However, if you stick to non-structural tetrahedral mesh, there are only intersection scenario between a tetrahedral element and the zero level set. In the scenario A, you have 3 intersection points, so you can connect those intersection points form one triangle, right? In scenario B, you have a 4 intersection point. For here, you need to make a choice and form 2 triangles, right? As you can see, this, local triangulation can be done in an element by element fashion. So it's super easy for parallelization, right? And after you get all the triangles, you build the connectivity, and you will have a triangulation for the gas metal interface. As I will show you later, this can significantly help you handle the laser material interaction. However, before I talk about that, I want to show you a side benefit of this mixed formulation, which is the geometric-based redistancing. So level set is widely used in multi-physics and multi-phase flow simulation. But as I mentioned, right, essentially level set function is a sign distance function. However, when you simulate the problem due to strong convection, right, this sign distance property may be lost. So what people typically do is to solve the so-called Epler equation to recover the sign distance property. However, in order to do so, right, although it is a very popular approach in the community, you need to develop a PDE solver, and there are so many numerical parameters you need to carefully choose in order to achieve best performance. Now you remember that our zero level set, right, or the gas metal interface is represented by a triangulation, right? So you can directly compute the distance function between a mesh node and the gas metal interface. Okay, and you can, of course, you can use a brutal force approach, which will give you the complexity of ON, where N is the number of triangles, right? But you can also develop some octree data structure to store the triangles, and you can reduce the complexity from ON to O log. So we actually compare the performance of this PDE-based, of this geometric-based redistancing and the PDE-based redistancing. And actually this, our PDE, geometric-based redistancing outperformed the PDE-based redistancing from several multi-phase flow problems, as we summarized in the paper 3 years ago. So now let me show you how you use this mixed formulation to handle the laser material interaction. So what we do is as follows, right? For a given laser profile, right? This depends on which laser model you use, right? We divide the laser profile into multiple rays. And for each ray, we will track all the intersection points between the ray and the gas metal interface. Now again, right, it's very simple. Your gas metal interface is represented by a bunch of triangles, right? So this ray tracing can be done in a pure geometrical way, which is truly simple. And at each point of the intersection, right, how much energy is absorbed and how much energy is reflected depends on the inclined angle as well as the material properties, right? And we trace the every intersection point between the ray and the gas metal interface until either the ray leaves the melting pool or the ray energy becomes sufficiently small. And at each intersection point, right, the absorbed energy will be distributed around the intersection point within a Gaussian profile. And we do this process between every ray and the gas metal interface. We will get all the Gaussian profile, we add them together, and this becomes your final heat source, right? And this final heat source will be converted into body force and turn in the energy conservation equation through the Bragg-Biot continuous surface force model. Okay. Now, this slide summarizes the key governing equations of the multi-physics model for metal additive manufacturing. So those equations, right, although they are very long, they are essentially conservation laws. So the first two equations are the conservation of momentum. The second equation is the conservation of mass. Those two equations are also the Navier-Stokes equations, right, over fluid flow. And then the third equation is the conservation of energy written in terms of temperature unknown. And then the last equation is the Neville-Set convection equation. And we solve this set of equation in a finely coupled way by using a stabilized finite element method. And we'll not dive into the details of this method. You can check our paper. So we consider all sorts of phase transitions during the printing process in the governing equation. One thing I want to bring your attention is that you can see that we consider all the critical boundary conditions, right? The interfacial forces and the fluxes, right, in our model. However, we still handle the model by using the Bragg-Biot continuous surface force model. You see, all the surface boundary conditions are converted into body force and turns. And those body force and turns will enter the conservation equations we are solving. I will dive into the details about this later in my presentation. Now, let's show you several applications, okay? I will primarily focus on validation and verification, okay? So the first one is a stationary melting process. So this is a fresh result from the NIST AM modeling competition 2022. So NIST, right, organized some blind modeling competition. So basically they run a set of experiments, they hide the result, they release the process parameter to models, and then you simulate the result, you submit the simulation result to them, and then they do the comparison to pick up the winners, okay? So let me show you what those videos mean, okay? So the video on the left, right, is from the X-ray imaging, right, showing you the melting pool evolution, and the video in the middle is from our simulation. And you can see that our simulation, our model, right, is able to capture the condition between the conduction mode to the chemical mode very, very well, right? And you can also see how the model captures the formation of a gas bubble and how this gas bubble is trapped in the resonified material after you turn off the laser. And this dynamic plot shows you the time history of the energy absorption rate, and then you see very good correlation between the experiment and the simulation, right? And this model wins 2 prizes from this modeling competition 2 years ago. But I know I talked to Wendan this morning. He actually got more awards. So that's it, right? So this department is really amazing. Of course, right? You can let the laser move. Okay, so let me play the video. So this is another simulation of one of the argon's experiments. Right? This is a selective laser beam melting process. You see very similar keyhole instability, right? And you also see very large free surface deformation in this simulation, right here. This will directly have implication on the surface roughness development. One thing I want to draw your attention is this those great fog type of thing, right? Which are the evaporation induced jet. This is a very important phenomenon. I will talk about this later in my presentation. This is another video you are looking from the top, right? Which shows you the surface roughness development. And those plots, right, shows you the comparison between the experiment and the simulation in terms of keyhole methodology, right? I mean, quantitatively, right, you see very good agreement. What else you can do, right? What else you can do with this model? Another important issue, as I mentioned, right, you see those gray fog type of thing, right? As I mentioned, right, those are the evaporation-induced jet. Sometimes those jets are very powerful enough to even blow away the mechanical powders. If those powders are redeposited on the substrate, they can cause lacular fusion and the rough surfaces. So in order to mitigate powder spattering, what people do is to apply the ambient cross-flow to clear the spatters. However, there's no modeling available in the community to systematically help you choose the optimal gas flow parameter to achieve the best mitigation strategy. The reason is that this is a multi-scale problem because the powder injection, right, happens at a powder scale, which is at a micro-scale meter. However, the particle dynamics in the AM machine chamber, right, subject to cross-flow happens at a meter scale, right? So you truly cannot simulate the two phenomena in one model. So recently we developed a multi-scale model that can help you systematically study this process. So what we do here is a very engineered approach. So we first developed a powder scale model to simulate the powder spatter injection initiation. So what we do here is we couple the mixed formulation with the DEM model to simulate, right, the powder injection speed and the injection angle. And after that, let me replay the video. After that, we do a parameterization of the velocity and angle of the particles, right? And impose them as the boundary condition at the bottom surface for the chamber scale. And the chamber scale couples aerodynamics and the discrete element method, and then take the information from the powder scale for powder injection initiation, and then the cross flow you apply to simulate the powder dynamics in the AM machine chamber. So let me show you how this model perform. Okay, so we did some experiment at UIUC. So this machine was donated by GE for education purpose. And I didn't show you the full machine, but it's a laser concept machine, I mean, very old version. This is the chamber of the printer. So we built a detailed CAD model for this AM machine chamber. You see, we pretty much resolve all the geometric details of that chamber, including printing platform, powder reservoir, cross-flow inlet, and cross-flow outlet. And this is the chamber scale model we built, right? This mesh for the chamber scale model we built. And this is only for the CFD. And you see that we even build a refinement region here, right? This region is to receive the detailed information, right, from the powder scale. Let me show you how this model does. Okay, so the video here, right, shows you the aerodynamics inside of the AM machine chamber, right? You see a jet, right? You see the cross flow, right? Applying here, going from here to here, and then turn around and here. If you look closely here, you will see a jet here, right? This jet is coming from the powder scale model, right? This is the information you received. And the video in the middle, right, showing you the following, right? You're looking from the top to the substrate. Those solid red lines show you the printing direction of the laser, and those blue dots shows you the dynamic process of the powder distribution. And we did some experiments, and here's the comparison, right? This is the powder spatter distribution extracted by a computer vision technique. I wouldn't say they are identical, right? Because there are several uncertainties we couldn't capture in the computational model, such as the initial powder bed distribution, right? But quantitatively, I feel it gives us some confidence to do some parametric study. So we pick up 3 important gas flow parameters to investigate, which we feel those are very important parameters. One is the flow direction, relevant relative to the printing direction. 0 degree, 90 degree, 45 degree. The second parameter is the flow rate. The flow rate is defined as the extraction level percentage of the maximum flow rate we are allowed to use by GE. We consider 20%, 35%, and 40%. And then we consider 2 different gas types. One is argon, another one is nitrogen. And here's the simulation result, right, for all the cases, right? So the left panel, right, shows you the final powder distribution by using nitrogen under different flow direction and flow rate. And the right panel, right, shows you the corresponding result by using argon, right? There are so many tendencies we can discuss, but one tendency I want to emphasize is that it seems no matter which flow direction and the flow angle, using argon always give you a better mitigation strategy as you compare, right? I mean, one by one, argon is always better. This is surprising. So we decided to do some very fundamental fluid mechanics analysis to rationalize this finding. So our basic concept is that higher aerodynamic force on the particle provides you better clearance effect, right? It's very simple. And if you open any fundamental dynamics book, you know that, right, the aerodynamic drag can be estimated as 0.5 times drag coefficient times the density of the gas times the relative velocity between the particle and the flow square and the frontal error of the particle, right? Now you also need to know in fluid mechanics, right, for flow past a particle, Reynolds number is not just a constant. It's a function of Reynolds number. So if you are in the low flow range or in the Stokes range, drag coefficient is inversely proportional to the Reynolds number. Okay, and if you plug this expression for drag coefficient into the aerodynamic drag formula, you see that for the same relative velocity magnitude and the same particle size, the aerodynamic drag is proportional to the viscosity of the gas. And if you open the periodical table, you will see the viscosity of argon is bigger than the viscosity of nitrogen. Okay. Now, if you are in a higher flow range or in the Newton's range for a sphere, right, the drag coefficient is a constant, 0.5. Now do the same thing, right? Plug into the aerodynamic force formula for the same particle and the same relative velocity. The aerodynamic drag is proportional to the density of the gas. And then again, you will see, right, from the periodical table, the density of argon is also higher than the density of nitrogen. So no wonder, right, no matter which flow range you are, right, which flow direction and which flow speed you use, right, using argon always provide better mitigation structure, right, for at least for this measure. So everything works seems good so far, right? However, there is an issue. I think the community, especially the computational multi-physics community, have been overlooking for a long time. This is how you handle the flux and the traction boundary condition, right? As I mentioned, right now, all the flux and the traction boundary conditions are handled by the Bragg-Biot continuous surface force model, right? This paper by Bragg-Biot in GCP is a well-cited paper, I think more than 7,000 or 8,000 times. However, in order to, although this, again, right, this method is very popular in the community. However, in order to utilize this method, you have to define the artificial interface thickness such that you can define the diffusive delta function here to convert the surface boundary conditions into body force and turn. So you can, such that you can throw those terms in the conservation law, right? I think everybody in the EM modeling community is using this approach. However, I think this can lead to significant error. So let me use this simple problem to show you that, okay? So let's just consider a pure conjugate heat transfer between a mechanical particle and a surrounding gas. Of course, this is a toy problem, but I want to show that this approach can lead to significant error, right? Because it's a sphere, very simple geometry, we are able to derive the exact solution of the temperature distribution, which looks like this. If you are using a diffusive interface approach, right? And then this result you get, right? And you see that result is over diffusive, right? And I need to tell you that I have already used 40 elements to resolve the particle. I think if Wenda is here, he would agree with me that if you use 40 elements to resolve a particle in additive manufacturing, this is considered to be really, really fine, right? So of course, right, for motor, you can always tune other parameters to match the experimental data. But this doesn't mean that the way you handle the boundary condition is rigorous and accurate, right? So we feel that we should do something fundamental to address this issue. So this is the motivation, right, of the coupled level set and the enriched immersive boundary method. So remember how we handle the material interface here. So what we do is we first use a level set method to capture the material interface evolution, right? After that, we do a triangulation for the material interface, right? So after this, we think if diffusive interface approach couldn't give you good satisfaction for the boundary condition, how about I use immersed boundary method, right, to impose boundary condition? This is a very natural idea because you already have a triangulation of the interface, right? However, I still insist on avoiding mesh motion and remesh because this is too complicated for many people. If you want to still have this feature, you need to resolve all the physical unknowns in the background. However, if you have studied finite elements, you know that for tetrahedral elements or for linear elements, right, you have a constant gradient inside, right? If you simulate a thermal process, the temperature gradient is a constant within the element interior. Now, if you have a material interface cutting through the element, if you just want to satisfy the flux compatibility across the material interface, as long as the conductivity for the solid phase and the fluid phase are different, because you have a constant gradient, right? This flux compatibility is never going to be satisfied, right? So this is never going to work for conventional immersed boundary method. So you need to do something special. So what we do here is this, right? After we immerse the triangulation into the background mesh, we will enrich the DOF of the nodes for the calcium, right? Which are those red triangles. We will enrich the DOF of those nodes by 1 for temperature field. So each of those nodes will have two temperatures. One is for fluid, another one is for structure, for solid. And then your solution representation is the interpolation by temperature TF and TS through a Heaviside function. But I need to tell you that this Heaviside function is a sharp Heaviside function. It's jump from 0 immediately to 1. There's no diffusive interface here, right? And then if you use this solution representation and you go through a augmented Lagrangian multiplier, you will have such a discontinuous Gaussian finite element formulation for this problem. And this approach, right, has several advantages over conventional level set and the conventional immersed boundary method. So let me show you them. So as I said, right, in conventional level set method, you need to perform redistension in order to resolve the sign distance problem, right? This is a common practice in multi-phase flow. And in immersed boundary method, the one non-standing issue is the small cut elements, right? Because you couldn't guarantee that, right, the interface will cut through the elements, right, equally, right? So small cut elements can cause instability, right, for computational fluid dynamics. However, in this coupled level set and enriched immersed boundary method, both issues don't exist. The reason why? The reason is because the special way we construct the triangulation, right? Because of that way, the nodes of the triangulation will be on the edges of the calcium. So because of this special configuration, I can always break the cut triangles into several small triangles, right? And then I can perform exact integration over those calciums. So you can see that if you do this approach, this small cut issue in standard conventional immersed boundary method can be greatly remedied. And secondly, when I do the integration over those small triangles or those partial points, I will be able to know exactly whether they belong to material 1 or material 2, right? So I don't need to do the use a diffusive Heaviside function to do the material interpolation. I can assign distinctive material property to the partial point in material 1 and the partial point in material 2. So you don't need to do level set redistance anymore, right? So which is very, 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 very nice. So let me revisit this benchmark problem by using this coupled level set and enriched immersed boundary method. Again, this is the exact solution, right? This is the enriched immersed boundary method solution coupled with level set. You barely see the difference, right? And then we also compare, the performance of this approach against, diffusive interface approach and the exact solution. And you see that, the enriched immersed boundary method agree with the exact solution very well and outperforming the diffusive interface approach, right? And this approach converged very well, right? Because I know that, many people don't trust modeling because sometimes they don't say, right, it's not reliable. However, this is because people don't perform mesh refinement study. So if you want to ensure the reliability of your model, you often need to perform refinement study to make sure that the results are converging. Okay, And we are also able to extend this approach to convective conjugate heat transfer process. So what you see here is the total flow past the hot sphere at Reynolds number 3000 and 700, right? This is a classical fluid mechanics problem. So for the fluid field, I want to show some validation, right? So this is a vorticity visualization to show the vortex structure behind the sphere, right? Very standard practice in fluid mechanics. And those plots, right, shows you the comparison between our approach and the direct numerical simulation using boundary fitting method, right? For the mean velocity, for the velocity fluctuation, as well as for the pressure coefficient prediction, right? So you can see that, right? Our model, right, deliver quite accurate result. And this video, right, shows you the cooling process of the sphere, right? You can see that, right? The temperature in the sphere is gradually decreasing, and those plots are the most important results, right? Those plots show you the relative error of the temperature flux and the temperature compatibility and flux compatibility on this sphere. And you see that if you are using the erased immersed boundary method coupled with level set, you can reduce the error to very low level, right? And if you use standard EIBM or immersed boundary method, this is what you get, right? You can see the accuracy of the boundary condition satisfaction is enhanced significantly. And we can apply this to a realistic problem, right? This is very straightforward, right? This is the CFD simulation, right? Of a gas quenching of a rotating aluminum gear, right? And as I said, right, everything is resolved in the background, right? No mesh motion, right? No remeshing, right? And because everything is resolved in the background. So the video on the left, right, shows you the temperature evolution in the flow, and the video on the right, right, shows you the vorticity. I just want to show you the turbulence, and the video here, right, shows you the full field temperature field, right, inside the gear during the quenching process. Okay, and you can also use this coupled level set and enriched immersed boundary method to handle the 7 boundary condition in solidification. Right, this boundary condition is really important in welding and metal additive manufacture, right? So the mathematical model for solidification can be summarized as follows, right? In the pure fluid domain or solid domain, you have the time-dependent heat conduction equation. And then on the fluid and solid interface, you need to satisfy the following boundary conditions. First, the temperature of the solid and the fluid need to be equal to the melting temperature, right? And then you need to satisfy the so-called 7 boundary condition, which tells you that the normal propagation speed of the fluid and solid interface equals to the flux jump divided by the solid density and the latent heat of fusion, right? So this is the 7 boundary condition. So if you solve the solidification problem using standard diffusive interface approach, what you will do? You will define an liquid fraction, right? This is everybody is doing in additive manufacturing as well, right? And then you convert the 7 boundary condition into a body force term, right? Into the energy conservation equation, right? To be honest, I think this is very straightforward. This is very easy to handle. If you use the coupled level set and the enriched immersed boundary method, this is the formulation you use. I agree that the formulation is way longer, right, than this approach, but what I'm showing is the variational form, right, for the fundamental formulation, right? So what we do here is this, right? We first use level set to convect the fluid and solid interface evolution, where the convective velocity for the level set UT is defined by the 7 boundary condition, right? The flux jump, right, divided by solid density and the latent heat. After we get the level set field, we extract the 0 level set, right, and form a triangulation. And then we immerse the triangulation into the background mesh to impose other boundary conditions. Okay, so it's a very simple idea. So let me show you how this method performs, right? So here we consider a very simple problem, which is the solidification of a nomini in quasi 1D, right? This is a benchmark problem from the textbook solidification written by Danzig and Rappas. Danzig actually is a professor at UIUC, and Rappas is a professor from EPFL. So this dynamic plot, right, show you the comparison between different methods. Again, this is a quasi 1D problem, right? So we are able to derive the analytical solution again. So those figures, right? Those are curves, right? Shows you the temperature distribution over the domain, and those vertical lines, vertical dashed lines, shows you the evolution of the fluid and structural interface, right? Or the position of the fluid solid interface. And you can see that the enriched immersed boundary method, right, coupled with level set, give you very good agreement, right, with analytical solution. However, if you look at diffusive interface approach, then you see the discrepancy, right? For both the temperature distribution, right? So far it's good. Later on you will see, right? I mean, the discrepancy will be bigger and bigger. And also for the fluid and solid interface position, right? You see very good discrepancy. And you can also extend this problem, right, to, you can also apply this approach to some realistic printing process, right? So the video you see here, right, shows you the simulation of one of the NIST AM benchmark 2018. This is the first version of NIST AM bench. And for so far, right, we only consider, I mean, thermal process, right? I mean, melting point fluid dynamics is not considered yet. But I want to use this video to show you the capability of this coupled level set and the enriched immersed boundary method. So in this simulation, we are able to maintain a explicit interface representation, explicit representation for the fluid solid interface without doing any mesh motion, any remeshing, any level set redistancing, and with a perfect Stefan boundary condition satisfaction, as you see from the comparison between with the experimental data in terms of melting point dimensions, which I show here, right? So I feel that, right, this approach, although we haven't fully finished it yet, right? But through several applications like quenching and additive manufacturing, I do see its potential in several applications, right? Involve interface coupled multi-physics progress. So with this, let me summarize my presentation, right? As I mentioned, simulation and the modeling of additive manufacturing is really challenging. And in order to overcome some of the challenges, we first developed a mixed diffusive-sharp interface approach, right? And our goal, right, technical goal is to maintain mesh flexibility, no mesh motion, no remeshing. And we also want to have an explicit treatment for the laser material interaction. And I also show you applications of this model by predicting the melting point, fluid dynamics, thermal history, defect formation, propagation, and the powder spectrum. And lastly, right, I show you some preliminary results for coupled level set and the enriched immersed boundary method. And one thing I want to emphasize is that those models are very general because we have fully control of the code, right? We can do any modification as we want. So we can easily modify the code and apply them to other metal AM process, such as direct energy deposition, or some conventional manufacturing process like quenching, autoclave process for composites materials. It should be super easy for the method I'm presenting here. So thank you very much.
You showed us, yeah, this is a challenging problem for sure. You showed some equations where you had Navier-Stokes for the metal melt, I suppose. And do you have a solid model, or once it solidifies, it becomes rigid?
Yeah, this is a very good question. So let me go to that slide. Yeah, I did.
You all have it memorized. Come on.
Okay. Yeah. So we model the process from a fluid mechanics approach, right? So when the material is in the liquid phase, it is governed by the Navier-Stokes equation. We are using the real viscosity of the liquid metal. And once the material is resolidified, right, we still use Navier-Stokes equation, but we just assign a super big viscosity to kill the material motion there. Yeah,
okay. And then there's the second question.
Right.
Again, this is not my field, but how good is a model, Navier-Stokes model for melted metal?
Right.
Is the Newtonian fluid a good model for that?
Oh yeah, this is a very good question. I think I think Newtonian flow is a sufficient assumption.
Yeah, but is that based on?
Based
You know what I
on
mean, like other experiments, which you know, like.
I should provide some justification, but I mean, what I can tell is based on the validation cases, right, for different people's model with experimental data, because all of those models.
I mean, it makes sense to me, but
Right.
it's just like, you know,
I know what you mean.
very impure, like ad hoc.
Ad hoc, I totally agree with you, right.
I had a Mercury toy when I was a kid, right, you know, it was like.
That's right,
very
that's right.
fluid,
Very fluid, yeah, that's right.
Believe it or not.
That's true, that's true.
Still okay though.
Yeah.
So thanks for.
Yeah, thank you.
Questions?
See, you have been doing all this, I would say for a decade or so, but what would be your suggestions for someone who would want to learn doing these modeling stuff? How should they go about it? Or what are some resources they can use to learn some basic fundamental things so that they can apply and learn from them?
Oh, I see. So I think if you want to develop your own code, right, the learning curve can be quite long because you see, right, you need to at least know how to handle the material interface overloading, right? How to write a finite element code, how to solve a Navier-Stokes equation, right? But there are some open source code you can leverage, right? Such as OpenFOAM, although it's based on finite volume. I'm using finite element. And if you just directly want to use the model and solve some practical problem, there is a software called Flow3D. There is a module for Metal EM, so you can use that software. But again, if you want to have your own modeling capability, so you can change, modify the code, right, as you want. I think you can start with some open source multi-phase flow model and gradually add in temperature field and other things. Yeah, but it takes time. I don't know whether.
No, that's a good suggestion. So because I have been using Console, for example.
Yeah.
But yeah, I mean, including multiple layers to it, multiple modules to it,
Yeah.
to a single model, it becomes very complex.
That's true. Yeah, I agree with you. I think the challenge is because when you integrate those modules in the conventional software, the coupling typically is quite loose, right? You solve maybe the flow field and then you solve the temperature field, but you don't couple them to do iteration to make sure both of them are converged, right? So this is challenging for commercial software. But if you use some in-house code, right, or source code, I mean, you can easily do that, right? You can do the iterations between two modules, right? Yeah, or you solve them together in a fully coupled way.
So thank you. This is a very wonderful talk. Gundan is doing solving the same problem using
Right.
different approach.
Right.
So this is a very fluid,
Right.
fully central
Right.
approach.
Right.
So there are two questions. What's the advantages
Oh yeah.
of this? You mentioned about GPU.
Right.
What's the connection of the GPU
Ah.
to your model? I think there could be some
Okay.
competitive advantages of this.
Okay.
And I'll probably keep the second question then.
Okay. Sure.
Yeah.
I think maybe I didn't make it clear. I think I only for the night displacement I'm using GPU for acceleration, but for the models here I'm still using MPI, Open MPI for the parallelization.
Okay.
But I still want to answer you the question of our model, right? As the advantage of our model. So I mentioned a lot of advantages of the model over some methods, right? Not a specific model. I think one significant advantage is it greatly simplifies the time for the users for model preparation. Because you just build a box, right? And then you can track the complex interface with an explicit representation, right? So what do you do for the models? You just build a box, mesh it, and then you can still capture the interface overloading, right? This is the big deal, right, in my opinion.
Yeah. So so this also
Yeah.
The model is accurate enough, so you
Right.
can win the NIST
Right.
competition, which I do know a little bit of them. It's not easy because there are many model results that come in. Then still go back to my second question was asking about do you segment and try to solve using the GPU? Obviously, you are not really.
For this one, we haven't done yet. Yeah, you're right. Thank you, Professor.
Yeah.
But that's something we're considering as well, because I think I talked to several professors, they want to use their model for their control, right, for the optimization. If your evaluation tool is very slow, it's coming very hard for control and the optimization. So one direction of course is through GPU. We also work on leveraging the high fidelity simulation data to develop a surrogate model or reduced order model, and which sacrifices accuracy a little bit, but provides better efficiency.
So just to follow up a bit, so you've already added a lot of physics
Right.
to your models.
Right.
But there's always more to add, right? If I want to consider the vaporization and
Yeah.
pressure,
Yeah, yeah.
particle shape,
Right.
and I can give you 10 more of these details. So if you think about it, do you see the future as making your model more and more sophisticated and using bigger computers, or like you said, doing reduced order modeling?
I don't know. I mean, this truly depends on the need, right? I mean, if you haven't understand the details or the physics, probably high fidelity model are still necessary, right? Although it's painful, but you better still add the physics here, right? Or if you have some understanding, I think for practical problems, I think efficiency probably is more important, right? Especially for industrial users, right? So I think we should go in both directions, in my opinion. But I agree with you, there's no end. Maybe you want to add magnetic field, acoustic field, right? It's hard.
I see. So maybe one final question for those of that comes from the finite element class. You make such a big model,
Yeah.
and then you said you use the stabilized version of
Right,
finite
right,
element. Is it very hard to stabilize these simulations?
I think when I mentioned stabilization, right, is mainly for the turbulent flow, right? Because you truly don't want to go with direct numerical simulation, right? I think you're kind of a fluid mechanics person, right? You know, direct numerical simulation needs really fine match, right?
Right.
So stabilized method is more like a model that allows you to obtain reasonably accurate results using relatively coarse. And typically, what I mean relative coarse measure is LES level, right? So right, stabilized method, I mean, also called sometimes variational multi-scale method, right, by computers, right? It's a LES model, right? So yeah, I don't know.
Oh, okay.
Yeah.
So is that what you did though, to stabilize it?
Yeah, that's right. We stabilize through SUPG, PSPG, right? SUPG, yeah, that's right. You need them. Yeah, it's I mean, especially if your mesh is not very fine. I mean, you can see from the previous slide, right, where it is. Right. So here you see the resolution. Although it's quite dense, right? But compared with DNS, it's still coarse scale, very coarse scale.
Oh, we have an online question from Zoom. So we have Ziyang Huang asking about the enriched immersed boundary method. So they don't understand how the method address the small cut cell issue.
Okay, I see. I think this is a very good question, right? So a small cut issue is a big issue in immersed boundary method. I think what I'm showing here is I mean, I should say, I mean, as what I said during my presentation is we remedied this issue, right? But I didn't say we completely resolved this issue. I think the reason is because if you look at here, the nodes of the immersed triangulation are on the edges of the background cut cell, right? So we can break the triangles, right, the bigger triangles into smaller triangles. And then because, right, you have those standard triangles, and then you can apply Gauss integration, right, for standard triangle elements to do the exact integration over those small triangles, right? So that's what I say is this small cut element issue is remedied. Do I answer your question?
Yes, so one more follow-up question is you do have extra cores to refine the mesh, right? But it's not everywhere, I would say, but it would be around the 0 level set, right?
Exactly, you're right. You're exactly right. Yeah, that's right. So we only have enriched the DOF, right, around the tarsal, right? Those red triangles, right? Those blue dots, right? The DOF are enriched. Yes.
Okay, I see. Okay, so all your like the level set triangulation is pretty much like adding some loads along the element edge, right?
Right,
So
right,
it
right.
won't cross the element node.
Yeah.
So that's how the method. Okay.
That's right. So because right, those nodes, right, for the triangulation or those crosses, right, are on the edges, right, of the background element. They are never going to be inside of the tarsal, right? But for conventional immersed blaster method, it's not guaranteed, right? The node of the immersed surface can be in the interior of the element, right? And sometimes they can cause some instability issues.
Okay. Thank you.
All right, let's thank the speakers again and